guys. So just a quick recap of what we have been doing. In fact, we are doing some serious business for the past few classes. We are analyzing sequential circuits. There are two methodologies of analyzing or designing sequential circuits. For the first 5 minutes, let me summarize what is about the analysis of sequential circuit is. Normally, either you will be given a sequential circuit and you have to draw the state diagram. Okay, so there are two kinds of problems that we discussed. You are given a circuit diagram. Instead of saying a circuit diagram, it is apt to say a sequential circuit. If you are given a sequential circuit, then you have to create the state diagram. Okay, so this is one methodology of problems. Other is you are given a state diagram, you have to create the sequential circuit. As design engineers, you must know both the methodologies. I'll just explain both the ways may be using this state table. Okay, the first method, if you are given a sequential circuit, then how do you make it a state diagram is, how do you design a state diagram is, from the sequential circuit, you will get the flip-flop input equations. From the diagram itself you can get, so you will get the flip-flop input equations. Now, once you have the flip-flop input equations, you can create the state table. Right now, the difference in filling up this particular state table is very important in both the process. When you fill up the state table, always you will fill up the present state and your input values with all possible input combinations. You have two present states and one input, then you will have 7 input combinations. This is the first few columns that you will fill. The next few columns that you will fill will be the flip-flop input equations in this particular process. And finally, you will fill the next state equations using the characteristic table, and then you will create the state diagram. Whereas in the next process where you are given a state diagram and you have to get the sequential circuit, what you will do is you will create a state table, right? And this particular state table will have only present state and next state only, which means that you will have the present state and you will have the next state. You will have to fill up the flip-flop input equations, and in order to fill the flip-flop input equation, you will use the characteristic table of the corresponding flip-flop that you are going to design. Normally, when you are filling these flip-flop input equations, you will have some don't care variables coming across at different places because of the characteristic table. Because your what is your characteristic table? It has got your present state and state. You will fill up the flip-flop input equation, and from the flip-flop input equations, let us assume that we have created the state table. You will have k map to some hold. Okay, so there was some. My screen is visible.
Yes, sir.
Yes, sir.
Okay, there seems to be. All right. So uh, once you have the equations for your flip-flop inputs, then you can easily create your sequential circuits. Okay, so this is the process you have to follow when you are given a sequential circuit and asked to make a state diagram, or you are given a state diagram and asked to make a sequential circuit. So we did a lot of examples in analyzing the state table. Now we are slowly, hello, yeah. So now we are slowly moving on to how we are going to optimize this particular process. Okay, normally at particular times you might come across different states also. Now we are going to focus upon the state reduction. What I mean by state reduction is, please note that these are the different states we have. What are the states we have? We have 0, 0, 0, 1, 1, 0 and 1, 1. So 4 states we have, right? So at times what happens is, say if you are counting from 1 to 7, then 4 states, 1 to 3, then 4 state, you can use 4 different states. If you want to count from 1 to 7, then you can use 3 states. 3 states in the sense starting from 0, 0, 0 till 1, 1, 1. Why I am saying every time I have to count from 1 to 3, 1 to 7? Because especially these flip-flops are used as counters, or these flip-flops are used for moving from one state to the other, which are sequential states. If you want to count from say 1 to 32, then the number of flip-flops that you will require will be, number of states that you will be requiring will be, that is 5 different inputs, right? 1, 2, 3, 4, 5, 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, right? So you will have so many number of states. So 32 different rows you will be having. Most of the times you will see that out of the so many input combinations, we will not be using all input combinations. We will be using only till certain things. Say for example, you want to count only till 1 to 20. If it is 1 to 15, then you will need 4 binary bits. If you want to count anything beyond 15, then obviously you need one more binary bit, which means that you have the capability of counting from 1 to 32, but out of the 32 countings, you are going to use only 1 to 20. So rest of the input combinations are going to be unused. So under those particular circumstances, we have a slight ray of hope that you can reduce the number of flip-flops. Why am I focusing towards the reducing the number of flip-flops? Because lesser the number of flip-flop, we have lesser the cost of our circuit. So now we are going to look at how to look if there are some unused states in our design. If you have a circuit with m number of flip-flops, when I say that I'm having m flip-flops, maybe I'll replace this m with some number. Say I'm having a 3 flip-flop. Okay, it means that 2 power 3, which is 8 different states are possible. Okay, as I said in the example, maybe you can see it here also, that here I'm having 8 different, I'm having 3 binary input combinations. So if I'm having 3 binary input combinations, so 8 states are possible here. Okay, so there are conditions when a sequential circuit may be less than the maximum number of states. So here the maximum number of states allowed is 8, but in a sequential circuit, you might be using only till 5 states. So the remaining states will be you called as an don't care states or an unused states. Okay, and these unused states can be treated as don't care conditions. Let us take an example of a state table with unused states here. Now, the present state has got 3 binary input variables A, B, and C. Similarly, the next state will also have A, B, and C. This state table is being designed using an SR flip-flop. Can anybody tell, on looking at the state table, whether it is a state diagram to a sequential circuit or sequential circuit, or a sequential circuit to a state diagram design? Can one of you tell, looking at the state diagram itself? Is it the first design or the second design? I repeat my question. On looking at this state diagram, can you tell whether this state diagram pertains to a design where you are given a state diagram and you have to find the sequential circuit, or you are given a sequential circuit and you have to find the state diagram? I hope my question is clear. Anybody quickly? Quick answer, please. We don't have time. We are running short. At least those who have been sincere enough. Very hard. No answers again. There is our file. No answers. You see here, you have present state, you have next state clearly written, and you will come across these don't cares only if you are doing the first design where a state diagram is given and you have to create a sequential circuit. So when you are given a state diagram, you will have present state, you will have next state, and you will have input. Okay, and you can create output also, right? So which means you are following the first design with where your state diagram is given and sequential circuit is you have to create. So only in this particular design your flip-flop inputs will have don't cares, otherwise you will not have don't cares. Okay, right. Okay, you are all listening very well. You are encouraging me a lot. Thank you. So now now if you look at this particular state table, right, for three binary input combinations, there 8 possible states are possible, right? So but how many states are there? I'm having 0 0 1, I'm having 0 0, sorry, 0 1 0, I'm having 0 1 1, 1 0 0 is possible, 1 0 1 is possible. So which means I'm out of 8 different possible states, I'm using only 5 states in fact. And that is why I've written it here also. This is the given part and this is the derived part, which means this corresponds to the first design. State diagram to sequential circuit. Okay, out of these used 5 states, what are the unused state? If you look at this diagram, 0 0 0 is unused. Okay, and 1 1 0 is unused, 6 is unused, and 1 1 1 is unused, right? Whereas 0 0 1 1 0 1 0 0 1 1 1 0 0 and 1 0 1, they are all used. Now, along with this three different unused states, if you combine this input column also, if you combine this input columns also, now this becomes a 4-bit operation. Now, including the input, now this is a 4-bit circuit now. So if it is a 4-bit circuit, along with the unused states 0, 0, 0, 1, 1, 1, 1, 1, 0, if you combine this input combination can take either 0 or 1. Then following 6 minterms are possible, right? So if 0, 0, 0 is an unused, with combining the input, either it can be 0 or it can be 1. Similarly, 1, 1, 0 is one unused state. So combining your input, either it can be 0 or 1. So you have 6 more additional minterms that are unused here. Okay, so these states can be treated as a don't care conditions. Okay, obviously you will be doing the same thing because you will have to get the flip-flop input equations. You will be getting the flip-flop input equations for SA, RA, SB, and RB, and SC and RC, meaning that there are 3 flip-flops. This is one flip-flop, second flip-flop, and third flip-flop. So you will be needing 3 different flip-flops here. Okay, so you will have, when you write the flip-flop input equation, obviously you will put the don't care conditions for unused. So you can see here that the purple colored X's are don't cares which are derived from these particular states. So what is the 0 0 0 corresponds to? Okay, the blue ones. 0 0 0 corresponds to the don't care. 0 0 1 corresponds to the don't cares. And similarly 12, 13, 14, and 15, these corresponds to don't care. So you can use it to your advantage and getting your input equations of your flip-flops, SA and RA for the first flip-flop, for the second flip-flop, and for the third flip-flop. You will see here that all the K map has got their don't care conditions filled exactly. So there they are considered to be don't care states. And similarly for the first one, these are the don't care states. Okay. All right. Now, and once you know the flip-flop input equations, you can draw the circuit diagram. That is why I asked this question, whether are you given a state diagram or you are given a sequential circuit based on the state table that I showed you, right? Then you can create the sequential circuit. Now, let us look at how to reduce the number of states, right? Now, this gives us a hope. When you have so many number of don't care states here, when you have so many number of don't care states here, this gives us a hope of reducing the number of states also. Now, the next part of our topic, we are going to look at how to reduce the state reduction, the number of states. If you want to do the state reduction, then you must follow a certain algorithm. I'm going to teach you that particular algorithm now. But before that, why do you want a state reduction? Any design process must consider a problem of minimizing the cost for your final circuit, right? So that is what is the objective, right? If you are designing something, you must give the cheaper product. Okay, if you want to have a cheaper product, at least in digital design here, either the number of gates that you use must be less or the number of flip-flops that you use must be less here. Now, since we are looking at a state reduction, states are directly proportional to the number of flip-flops. You have 3 states, then you will require 3 flip-flops. Or in fact, the number of flip-flops are directly related to the state reduction problem, in fact. So in the previous example, you see how many input variables we had, the state variables. We had 3 state variables, A, B, and C. So the number of flip-flops required are 3 flip-flops are required. Okay, if you have 5 different state variables, then you will require 5 flip-flops. So the number of state variables and the number of states that you are going to have are directly related to the number of flip-flops. So now let us look at the algorithm now. What is the algorithm? Now, what you must keep in mind is the number of states are immaterial in uh, state reduction problems. Always what you must keep in mind is what is your input, what is your output, and if you are giving this particular input, is it going through a proper state, and then you are getting the output. This is what is important when you are doing the state reduction process. Okay, so that is what is written here. Concerned with the procedures for reducing the number of states, state reduction algorithm is concerned with the procedure for reducing the number of states in a state table while keeping, this is important, external input and output requirements are unchanged. That is, input and output must never change. Okay, so m flip-flops will produce 2 power m different states. A reduction in the number of states means it is reduction in the number of flip-flops. Okay, so which means if there are 2 power m states are possible. Let us take a practical example. If, say for example, I have 15 states. If I have 15 states, or including 0, let me take, if I'm having 16 states, then the number of flip-flops that is required is I will need 4 flip-flops. If I'm able to reduce the 16 states to 10 states, still I will need 4 flip-flops. Okay, so the cost reduction we cannot always guarantee every time. Only if we reduce the 16 states to say 7 states or 8 states, only then we can reduce the flip-flop to 3 number of flip-flops. Okay, so what does this mean is state reduction will always never guarantee the reduction in the number of cost, but it can definitely guarantee the reduction in the execution time. When you have 4 number of flip-flops and you have more number of states, right? There is always a risk that these particular states will enter some unused states also. So if you reduce the number of states and if your logic is crisp enough, then it is going to circulate only among those particular reduced. Now we will see an example where we are going to reduce the states, but that particular state reduction will not directly materialize in the reduction of the flip-flops. So let us see one example now. So as that is mentioned here, sometimes equivalent reduced circuit may require additional gates also. You may reduce the flip-flop, but the logic of the combinational circuit, the number of gates that you use might increase. Okay, so let's say an example. Now let us take this example. So this is a, what is this? What diagram is this? This is a state diagram, which tells you the different states that you are having. How many states you are having? You are having A, B, C, D, E, F, and G. So how many? 1, 2, 3, 4, 5, 6, 7 states we are having. If you are having 7 states, then how many flip-flops we will need? We will need 3 flip-flops. How did I do it? What is 2 power? What 2 power something is equal to 7, right? I mean, it will be 8, obviously, right? So 2 power 3 makes it 8. So 3 flip-flops are required. Okay, so we are trying to reduce the number of states from 7 to, at least if you reduce it to 4, then you can reduce one flip-flop. Okay, now we are going to apply the algorithm. Please again see that this state reduction will always not guarantee the reduction in the number of flip-flops, but it will definitely help in the reduction in the complexity and the logic and the timing diagram for the circuit. Okay, now what you must keep in mind? What you must keep in mind is that as movement of one state to the other is immaterial, but your input and output combinations should not change. So that's what it is clearly written here. In this example, only the input and output sequences are important. Internal states are used merely to provide the required sequence, but it is not really very important. So far in all the state diagrams, you must have come across that our state diagram looked something like 0, 0 moving to say 0, 1, 1, 1. It is moving to 1, 0. It is moving to 0, 1. Something of this kind we were always seeing. But here, just for the sake of convenience, instead of a binary variable, we are giving some alphabet variables for different states so that it gives us, it makes it easy to visualize and makes it too easy to analyze the state diagram. Hence, instead of a binary value, some alphabet values are given for assigning the state values. So A, B, C, D, E, F, and G are the different states we have. Now we have to look at what is the input sequence, what is the output sequence, and how is the state transition is taking place. In order to do that, we have to create some kind of a table. So it is not really a table now. I'm just going to zoom out so that you can visualize. Okay, maybe I'll explain it in a different way. Okay, what is that we are going to do with this particular state diagram is I'm going to give a certain input sequence and I'm going to follow how the state transition is taking place. Now that particular input sequence is this one 0, 1, 0. So consider the input sequence 0, 1, 0, 1, 1, 0, 1, 0, 0 starting from initial state A. Okay, so I'll write here so that I need not go bottom to explain again and again. Okay, now what is the sequence? 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 0, and I'm starting from A. Okay, now let's look at the diagram. Now I have to start from A. Okay, should I'll use this pen. Okay, now I'm giving an input of 0, right? So I will be in state A, right? Because giving a 0, I'm going to be in state A. Then I'm giving 1. If I'm giving 1, where am I going? So if I'm giving 1, I'm moving to state B because this is 1 here. I'm moving to state B. And once I'm in state B, so I'm in state A here. Now I have moved to state B. Then I'm giving an input of 0. If I'm giving an input of 0, I'm moving to state C. I'm moving to state C. From 0, I'm giving an input of 1 here. Please note this is input sequence. I'm giving 1 here. I'm moving from state C to D. I'm moving from state C to D. Then from D, if I'm giving an input of 0, I'm moving to state E. Okay. And additionally, I should also note what must be my output. Okay. When I'm in state A and my input is 0, what is my output? My output is 0. Similarly, when I'm moving to state B, my output is still 0. When I'm moving to state C, still my output is 0. When I'm moving to state D, still my output is 0. When I'm moving to state E, my output is 0. Okay, now I'm in state E. From E, I'm going to give an input of 1. So I'm moving to which state? F state. Right? Okay. And what is my output? My output is 1 here. From F, I'm giving again 1. Still, I'm going to be in the same state because 1 will not make me to move to any other state. I will be state F, and again my output is 1. From 1, that is from the F state, if I'm giving an input of 0, I'm moving to G state. And what is the output? My output is 0, right? So I am moving to F, and then I'm still here. Then I'm moving to G. Okay, my output is 0. Now from G, if I give 1, I will move to F state. I will move to F state. And my output is 1. From F, if I give 0, I will move to G. Again, I'm moving to Z and my output is 0. And from G, if I give an input of 0, I'm moving to which state? I'm moving to A state and my output is 0. Understood how I have created this table, right? So these are my, I should reduce the width. This is my present state or state moments. Okay, so when I'm in A, which is my present state, my next state will be B. When I'm in B, which is my present state, my next state will be C. So on looking at the state diagram, I'm going to create a table or a state table, something like this, right? I have created a state table explaining about the movement of different states. Can you visualize what we have done? Right? It is the same thing. A, B, C, D, E, F, F, G, F, G, A. Right? You can see that also. A, B, C, D, E, F, F, G, F, G, A. Right? The same input sequence. And the output sequence also 4 times 0. This is the starting point. That is the reason. 4 times 0 and then 110100. So 4 times 0 start 110100, right? So we have created the uh, states input and output sequence from the state diagram. Okay, having created this particular table, now we have to create the actual state table. How do we create the actual state table? We all know how to create the actual state table. We will have a present state. We will have the next state. Between the present state and next state, we will have our input, and we will have, after the next state, we will have our output. From the diagram itself, I can create. If my present state is A and if my input is 0, what will be my next state? My next state will be still A only, right? And my output is going to be 0. If my present state is A and if my input is 1, I move to which state? I move to B state and my output is 0. If you want, I'll write it again in case you are not following. I'll write it again so that my present state is A. Okay, my present state is A. I'm giving an input of 0. I'm giving an input of 0. Okay. So what is my next state? My next state is A. So my next state is A. And what is my output? My output is 0. I hope I'm clear now. If my present state is A, if my present state is A and my input is 1, my next state is B. My next state is B and my output is 0. If my present state is B and my input is 0, my next state is C and my output is 0. If my present state is C and if my input is 1, my next state is D and my output is 0. Right? Likewise, can you fill? Right? So we have created the present state, input, next state and output. Please remember our objective is obviously the next process will be is you will create the flip-flop input equation here and then you will create the K-map and then from the K-map you will create the sequential circuit. But our objective is not that. Our objective is try to see if we can reduce the number of states. Okay. So if you look at the state table, this is how your state table is going to look like. Okay. How? I'm just going to flip through different files. Okay. So just I'll be slightly slow so that sync is proper. When my present state is A, same thing, but when my present state is A and my input is 0, I will be in A. When my present state is A, my input is 0, I will be in same state A. Right? I will be in same state A. And what will be my output? My output here is 0. Right? So my output here is 0. When my input to A is 1, this you can draw from the state table also. Instead, maybe you can go here, erase all the inks. Yeah, from here also you can see. Maybe I'll draw it here. I'll write it here. So your table, what present state, next state and output, right? So I have my present state, next state for different inputs, x equal to 0, x equal to 1. My output y for two inputs, x equal to 0 and x equal to 1. When I'm in A, when it is 0, I'm still in, sorry, when it is 0, I'm still in A and my output is 0. When it is 1, where am I moving? When it is 1, I'm moving to B and my output is 0. When I'm in B, when I'm in B, 0 makes me to go to C and 1 makes me to go to D. So it is C and D. I have to look at the output also, 0 and 0, 0 and 0. When I am in C, when I'm in C, 0 makes me to go to A and 1 makes me to go to D. A, D. What are their outputs? Again 0 and 0, 0 and 0. When I'm in D, when I'm in D, 0 makes me to go to E and 1 makes to go to F. E, F. And what are my outputs? When it is going to E, output is 0. And when it is going to F, my output is 1. Likewise, you will fill for E, F and G. Right? And this is what is the truth table that will look like. Any doubt till this? Please ask me. Any doubt?
No, sir.
Okay, great. Okay, so now what is our objective? Why did we do this? Because our objective is to reduce the number of states. Now comes the algorithm. What is the algorithm says? What is our objective? Our objective is to reduce the number of states. Please remember how many states? 1, 2, 3, 4, 5, 6, 7 states are here. We are trying to reduce it to. We are trying to reduce it. If it reduces still be less than 4, then we will use lesser number of flip-flop. Now, what is the first thing that we must observe to start reducing the states? Again, go back to the first statement of state reduction. Input output combinations is very important while reducing the states. Now, scan through the, if any two states are having the same next state and same output, then they are equivalent states. What do I mean by that? Look at A now. A next state is AB and your outputs are 0, 0. Scan through all the rest of the rows. Do you have AB and 0, 0, AB 0, 0, AB 0, 0? There is nowhere. So there is no state which is equivalent to A. Scan now come to B. Next state is CD and output is 0, 0. Scan through rest of the rows. If you have CD and 0, 0, then that particular row is equivalent. CD 0, 0. CD 0, 0, no states. So which means B is equivalent to nothing. C, let us see. AD and 0, 0. AD 0, 0, nothing. Then D, EF and 0, 1. EF 0, 1, EF, no, nothing. Then come to E, AF and 0, 1. GF is there. AF is there. Yes, GF 0, 1 and AF 0, 1, which means that E and F are equivalent to each other, which means that I can just replace this G with E. Okay, or even E with G also, that is okay. Because we are having alphabets A, B, C, D, E, F, G. It is always better to remove the last one so that we have a sequence till F. So we replace the last one with G. Okay, so wherever you come across G, replace it with E. Where do you come across G? Here you are coming across G, so replace it with E, right? Okay, so this is the first step is to find the equivalency. Second step is to replacing the different states. Now again scan through it. Do you have AB00? No. Again, when you do this particular process, you will again see some equivalency between two states. You see here, we are having EF01 and again we are having EF01. What does this mean? This means that D is equivalent to F. Sorry. Okay. D is equivalent to F. D is equivalent to F, then replace everything F with D. Okay, so we are having D, 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 and D. Again, repeat the process. AB, you don't have any. CD, do you have? No. AD, do you have? Yes, there are multiple ADs here. So I have to use a different color. Okay, so AD we are having here. C is equivalent to E. And okay, already we have replaced the last one, right? So which means now C is equivalent to E. Okay, C is equivalent to E in the sense replace all E's with C. So here we are replacing it with C. Here we are replacing it with C. And that's it, right? Okay. Further, can we? So we have reduced to 4 different states, right? A, B, yeah, this E will further gets reduced to C. A, B, C, D states. Okay, 4 different states. Okay, so this is, you will keep on doing this till you reduce these states, and I'll show you now the reduced state. Yes, yeah, this is the process that we follow here. And again, let me repeat. The first step is find the equivalency, and then second step is find the replace the equivalent gate. So G is replaced with E. So wherever you have G, replace it with E. And then the next step is G. You can see again, you repeat the process E and F, which means that D and F are equivalent. So replace this F with D. So this is the 5th step. And the 6th step is replace everything with D. Again, find out if there are equivalency. There are equivalency with C and E. Likewise, you have to keep on repeating. Now, the reduced states will be, these are the reduced states. Still, I'm in fact, yes, these are the reduced states. I'm going to ask you one question now. Here also AD and here also AD. I should have reduced, right? C and E.
Sir,
Why?
no, because the outputs are
Yeah,
different, right?
exactly. No one. When I did that before, nobody pointed it out. Okay, good. So, okay, where is the file? Yeah. Why we did not do this is our outputs are different. Here it is 0, 0. Here it is 0, 1. Okay, so hence we cannot reduce it. Okay, so now this is the reduced state table. Now, once you have the reduced state table, you can again redraw your state diagram. How? My present state is A. If I'm giving input 0, it is my input is 0, my output will also be 0. When my input is 1, I'm looking at here. When my input is 1, I'm going to state B. What is my output? My output is 0. When I'm in state B, when my input is 0, when my input is, okay, I'm sorry. When my input is 0, I'm moving to state C. Okay, when my input is 0, what is the output at that time? It is 0. And when my input is 1, I'm going to D. When my input is 1, I'm going to D. And what is my output at that time? 0. When I'm in, am I doing it right? Yes. Oh, no. I am doing it for B, right? So from B, I'm going to D when my input is 1 and output is 0. Now coming to C. When my input is 0, I move to A, 0. My output is 0. When my input is 1, I go to D and my output is 0. When I'm in D, I move to a new state called as E. When my input is 0, my output is also 0. I move, I will be in the same state if my input is 1 and my output is 1. Now from E, I move to state A if my input is 0 and my output is 0. And I move to state D if my input is 1 and my output is 1. So this will be the reduced state diagram. So the reduced state diagram is drawn here. Okay. Now you can follow the whatever the process that we did before. We already have the present state, next state, and the outputs also. What you can do here is insert the flip-flop input equations. If you are it all depends on the kind of flip-flop. If you are using a JK flip-flop, then how many flip-flops are required? 1, 2, 3, 4, 5. So again, you require 3 flip-flops. So you will have JA, KA, JB, KB, JC, KC will be the flip-flops. You will find the characteristic equation. Now, immediately you can ask me a question. We are having A, B, C, D, E. Then only if we have 0, 0, zeros and 0, 0, 0 for, then only we can write these characteristic equation, right? So then now what we should do here is we have to assign these alphabet variables with binary variables. Okay, so that is called as the variable assignment that we are going to see next. So yeah, next comes the state assignments. Now there are 3 different types of state assignments. I'm just going to directly jump. There are 3 different types of state assignments. One is a binary assignment, which is very straightforward, which we are very much used to it. Second is a gray code state, and third is one hot state assignment. What is this particular topic about? Because we are having states in terms of alphabets. Only if these are in terms of binary, we can write the flip-flop input equations here from the characteristic equation, right? So in order to do that, we are studying about the state assignments for different variables. So what is about binary assignment? Your binary assignment is nothing but we just assign binary variables in sequence to this A, B, C, D, and E, which means A is 0, 0, 0, B 0, 0, 1, C 0, 1, 0, E 0, 1, 1, and E 1, 0, 0. Now there is second kind of assignment which is called as a gray code assignment, where each successive states changes only by one variable. So if it is 0, 0, 0, next will be 0, 0, 1. And C will be 0 1 1 instead of 1 0, because in this particular case we are having two binary changes, so we need a gray code change here. So only this 0 has been changed to 1 and D has been assigned to 0 1 0. So only this binary transition takes place. And similarly, D to E is assigned 1 1 0, so that only one binary value change. So this is second kind of assignment which you can do. Third possible way of assignment is called as a one hot assignment. What is this one hot assignment is? Count the number of states you are having. You are having 5 different states, right? So you will have 5 different binary values. Okay, and each binary value will have only one in it. So if you are having the first state, we will replace 1 to it. And the second binary assignment will be B will have 0 0 0 1 0. But the number of binary variables that you have will be equivalent to, or will be equal to, the number of states you have. You have 5 different states, so this will also be 5-bit binary. Okay, so likewise, each one will have only one at any particular time. Okay, so there are certain advantages of each of these three things. What is the advantage of having a binary? Is it is the easiest and the simplest way, because it is equivalent to counting 5 integers, right? So this is the most simplest way. The advantage of gray code is you are having only 1 bit change here, so it is easier for your K-map simplification. Okay, then the last one hot assignment, you are having so many number of bits, but at the same time you are having only one in your binary bit variable. So if you want to do any decoding logic, then it will be easy with one hot assignments. Okay, so it is up to the designer to follow any method as he likes. So as far as this course is concerned, we will look at the binary assignment so that it is simple for us. So now let us complete the simplification process. So what we do is we are going to assign the first, we are replacing now this particular reduced state table, this one. We are reducing this particular state table using the binary state assignments, which means that A is represented as 0 0 0, B is represented as 0 0 1. So if the 0 0 1, C will be replaced with 0 1 0, D with 0 1 1. So C what? 0 1 0. A is 0 0 0. D is 0 1 1. D with again 0 1 1. E is what? 1 0 0. And D again with 0 1 1. E with 0 1 0 0. A with 0 0 0 and 0 1 1. So now your state table will look like, after the state assignment, it will look like this. Now you all know how to write, right? So these are for the 3 flip-flops. You definitely require how many flip-flops? You will require, because there are 3 assignments here, so you will require 3 flip-flops, A, B, and C. A, B, and C. So for 0 0, if it is a JK flip-flop, it is 0x. Am I right? A, JA, KA, JB, KB, JC, KC. For 0 0, it is 0x. 0 0, again one more 0x. So 0x. So similarly, you will keep on filling all these particular rows. Once you fill, create a K-map for each J and case. So there will be how many equations? There will be 6 flip-flop input equations here. Once you have 6 flip-flop input equations, you can easily generate your sequential circuit. Okay. So any doubts here? Okay, so this is the algorithm. This is called as the state reduction algorithm. And the next topic that we will see will be registers. I think this particular term you are familiar with. So we will look at what registers is all about in the next class. Registers is nothing but a combinations of flip-flop and some gates. Okay, so we will see what is a register is, and then how to design a register using flip-flops. We will see in the next class. Any doubts so far, because this is quite an important topic. state reduction is, and there is one separate subject in electrical engineering exclusively for the state reduction. So that is the depthness of this particular topic. One complete subject is there for state reduction alone in electrical engineering. Okay, so I think if there are no doubts, then we may wind up the class. Thank you so much.